Kia ora everyone. Today we are going to talk about three-phase motors. So in our last unit we looked at single-phase motors and we kind of worked through some of the fundamental elements of motors, how they operate and how they work. We're going to explore that idea a little bit more in this one here. Again, the fundamental interaction between magnetic fields that make a motor, any motor, turn, but obviously with a specific eye on three-phase motors as opposed to single-phase motors. There's a little bit of byplay here between three-phase and single-phase motors, right? Obviously they work essentially on the same principle, however there are some fundamental differences. You would remember in the last lessons when we talked about single-phase motors, obviously a lot of that was focused on how we make that motor start, because that's something that is difficult in a single-phase context. And we used the reference point there was the three-phase rotating magnetic field, which we saw was a true rotating magnetic field, whereas in a single phase supply we have that alternating magnetic field rather than a true rotating magnetic field. So if you're thinking about motors from that point of view, it actually probably make more sense to go with three-phase motors first, right? To understand that rotating magnetic field, that is a fundamental property of three-phase that makes a motor work, and then we look at how we adapt to an alternating magnetic field and add things like capacitors and various other devices which give us that phase displacement that we need to start that magnetic field, or start that rotation in the magnetic field that is so difficult with a single phase. However, we've gone the other way. We've gone single phase first. So we've got some of the more complicated stuff out of the way, and then some of the three-phase stuff is then a little bit easier to understand. We will, however, cover some other ground in here that's a little bit more complicated. So let's get into it and have a look at what we have today. So a three-phase induction motor is one of the most commonly used electrical machines in industry because of the following reasons. It has a simple design and impressive load characteristics. So simple design meaning, so like the as opposed to the single-phase motor, which had capacitors or various types of starting circuits, different add-ons that we need to make that motor work. Whereas in a three-phase motor, we don't need that. The three-phase rotating magnetic field inherently starts itself. So it's simpler in design in that respect. Impressive load characteristics. So again, that three-phase magnetic field gives us good torque for a range of situations. Electronic motor speed control makes it easy to control the starting and speed of three-phase motors. Construction is very rugged, and the motor has minimal moving parts. Again, we don't need centrifugal switches and stuff like that we have in our three single-phase motors. We don't need mechanisms to switch in and out our starting circuits. So means it's simpler. Three-phase motors range in size from small motors of a few kilowatts to huge motors of several hundred kilowatts that need cranes to lift them into position. The induction motor is by far the most widely used form of AC motor in factories throughout New Zealand. The reasons for that are it is reliable and easy to construct, it has no electrical connections from the supply to the rotating part, and it has good efficiency. So no electrical connections from the supply to the rotating part. So that should tell us something interesting about this type of motor, that the rotor itself has no connection. So we don't need any. Obviously, we don't need a commutator because it would be a DC motor, but in this case, we don't need any slip rings either. We don't need to put a field of any description onto our rotor, which again simplifies the construction, right? A general construction. The figure shows an exploded view of a typical three-phase induction foot mount and flange mount motor. That's just how the motor is physically mounted, either to the floor or to a machine. They consist of two main parts, a stator and a rotor. The additional components hold it together and provide cooling. Most of the components are of a rugged metal construction, with the rotor suspended via ball bearings between the end plates. So the rotor is just sitting inside the stator, not touching anything. It has shaft coming out either side, and it has a bearing on the end of each end of the shaft, which then attached to our motor housing. So it gives the ability for that rotor, obviously, to spin freely inside the stator. The connection box on the side of the stator, that's this guy here. Actually, let's make this bigger so we can see it a little bit more clearly. Connection box on the side of the stator is for terminating supply cables to the stator winding. So that's where our cables are going to come in here, and then it has all the connections in there for the stator windings. Fan is mounted on the rotor shaft to blow cooling air over the motor when it's operating. So there's our fan at the end of the shaft here, and then a fan cover you'll see has holes in the front of it or end of it there. So the motor itself, as it's turning, it's going to turn that fan and it's going to suck air in and cool itself. The motor is bolted down into position through bolt holes provided in the mounting feet or via bolt holes around the mounting flange. So there's our mounting feet there, and you can just sort of see that bolt hole just in there. Note that the rotor in this example is a squirrel cage type as opposed to a wound rotor. So we have a squirrel cage type there as opposed to a wound rotor. We'll talk more about that as we go along, but you can kind of see there that squirrel cage, just as a primer, that rotor there looks kind of solid. It doesn't have any kind of visible wires in it, whereas a lot of the rotors we would have seen have that familiar construction where we see that it looks like a lot of copper wires jammed into the rotor with the loops at the end, so it's going in out through the rotor. So that's what we're talking about, a wound rotor, as opposed to this one here is a squirrel cage. Three main parts of the stator are cast iron yoke. So it's just the outer part there, number one. It's not necessarily cast iron. In fact, cast iron is probably pretty uncommon these days, but it's a metal outer casing. Laminated iron core, which is slotted to hold the winding and has several holes to help cooling. So that's our laminated iron core in here. So that's so our iron core is like the core of our transformer, right? It's in there to facilitate the or magnifies and directs the magnetic field, I guess is a way to put it. The construction of that's a little bit different to what we would have seen in a transformer, because this is inside a motor, so it has slots cut into it to allow, as you can see, the windings around the outside. Now we have that, as I said on the last slide, that kind of familiar looped or braided copper. I've put a video on Facebook. You'll also be able to find this online if you want to on YouTube, the construction of a motor. Certainly encourage you to have a look and see if you can dig in a little bit into what is going on with those loops of copper in there. And that's our winding, and then we have the slots in the core to allow those windings to go through. So obviously number 3 here is, as I just said, that's our winding. Stator houses the laminated iron core around which the windings are distributed. That's an important point, the distribution of the windings. It is this winding that establishes the rotating magnetic field around the laminated core, concentrating the flux into the air gap between the stator and a rotor. The stator may be wound for 2, 4, or any even number of poles. So remember, just as a general thing, we're going to have 3 phases, so that'll give us 3 separate and distinct windings, which will be distributed 120 degrees apart. We know that we separate the windings by 120 degrees. If we separate the windings by 120 degrees physically, we will get 120 degrees of phase separation electrically. Well, that's for our generator anyway. Motor is the same, but in reverse. We have for 120 degrees of phase separation on an incoming supply. So therefore we must copy that by having 120 degrees physical separation in our motor for it to operate efficiently. The number of poles is a different thing. That's the number of times we see each of those phases within the winding here, or within the stator. So I could have 2 poles, which would just be, say, a red north and a red south, a blue north and a blue south, and a white north and a white south for the 3 different phases. So that would be 3 phases, 2 poles. But we could have multiple poles if we wanted to. Remember though that the poles, we can only ever have 3 windings. So if we have 6 poles, or if we have 4 poles, that means we have 4 of each of the 3 phases. Doesn't mean we've got 4 phases. If that's confusing, just put it aside. It's just a little thing of interest. The rotors, the 2 main types of 3-phase induction motor are the squirrel cage motor and the wound rotor, or slip ring rotor. A slip ring motor. Both motors get their name from the type of rotor used in their assembly. The squirrel cage rotor, this is by far the most common of the 2 rotors, called a squirrel cage because the winding looks like the exercise wheel used for hamsters and squirrels. You know the thing in the hamster cage, or squirrel cage, and it's got they run on the little wheel, and you got the bars across it. It consists of a stack of steel laminations with evenly spaced conductor bars around its circumference. The conductor bars are electrically and mechanically connected with end rings. A slight skewing of the bars helps to reduce audible harm caused by vibrations. The rotor and its shaft constitute an integral rotor assembly. So it's all stuck together. We have conductor bars rather than winding, so just metal bars. And then the metal bars are joined together at each end with an end cap. So then it looks like the hamster or the squirrel cage running wheel. There we go. And hence why it is called that. And here we go. Here's a little picture. The main part of the squirrel cage rotor are the laminated iron core, uninsulated winding in the form of a cage, and a steel shaft. So here are our conducting bars. So the conducting bars in this case are replacing the windings. There are no windings, we have the conducting bars. And then we have sandwiched in there steel laminated the core. So it's cut away there, but that core will go all the way across here. Laminated, just like in our transformers, to prevent eddy currents, to reduce eddy currents within the rotor. We don't want to waste energy having current racing around inside our rotor. That would be pointless. The figure shows an aluminium rotor winding in a squirrel cage form. This is cast into the laminated iron rotor core in one piece to form the complete rotor. The rotor winding can be made of either copper or cast aluminium with a connecting ring at each end of the cage. So then at each end, here and here, then we have a ring which connects all the conducting bars together. Double cage rotor, a special type of cage rotor designed to give a lower starting current and increased starting torque, is the double cage or Bouchereau mode. I have no idea whether I pronounced that correctly. It has an extra set of rotor bars forming 2 separate cage windings. The outer cage is smaller in cross-sectional area, so it has a higher resistance, and as you'll see later in this unit, this produces an increased starting torque. So there's our single cage, and here's our double cage here. You can sort of see there. Let's just make that bigger again. You can kind of see there the inside cage and then outside cage. While I think of it, access code for this test, first digit is 9. First digit of the access code for this test is 9. The wound rotor. The wound rotor consists of 3 insulated copper wire windings, star connected. So let me finish the sentence. Wound into slots on the laminated iron core of the rotor. One end of each winding is connected to an insulated slip ring mounted on the rotor shaft. So we have it here. So we have the windings connected in star. We're only ever going to have 3 windings. As I said, we may have multiple poles, but we're only ever going to have 3 windings in our 3-phase motor. It's star connected, which means that the ends, one end of each of the windings are all connected together. That would be our neutral point if this was a generator or a transformer. And then our windings go out from there and they're connected to the supply. So in this type of motor we have, slip ring. So earlier on there was a slide and it said we don't have any electrical connection to the motor. That's for our squirrel cage. For the wound rotor, we're still going to have that connection. So we have our slip rings here, which are on this one here. That's a really nice example there, isn't it? Because you can just imagine the carbon brushes sitting directly on those slip rings there, providing that nice connection, and then our 3 phases coming in will connect to the carbon brushes. So that's how we're going to get power into our rotor there. And then each of those 3 slip rings, it's very obviously 3 separate slip rings there. Each one will be connected to one of the phases, and then they'll each also be connected to a winding inside the rotor here. And then the other end of the windings will all be connected together. So that's how we get our star connection. So what's going on this one? Well, it's obviously something different. We'll talk about it more as we go through, but you should be starting to think, oh, hang on, that's quite different to what you just said about no electrical connection onto the rotor. And you're right. So we're actually going to have a magnetic field existing in here. So what's happening there? We're going to see an interaction between 2 different magnetic fields, one on the stator and one on the rotor. Yeah, the wound rotor. Brushes bear on the slip rings to connect the rotor to external resistors, which during the starting period reduce rotor current and hence stator current. They also improve the rotor power factor so that the current is much more effective in producing a torque. The resistors are cut out in steps until finally there is no external resistance in the rotor circuit, which means the slip rings are short-circuited when full speed is reached. The motor will then behave as a normal cage rotor. So normal cage motor, no electrical connection to the rotor. Why do we, as I just said on the last slide, hang on, now we're saying we've got a motor with a rotation, with a connection to the rotor. So this is part of starting. Something we know, and we've talked about this in the last unit, we've talked about it previously, we've seen it, I think most of us have measured it, that a motor will draw higher current on startup. And so there's two issues we have there. One is that the motor inherently as it starts will draw a large inrush current. That just is what it is. And also the fact that depending on the application of our motor, we may not want it to try and hit full speed immediately. We may want a ramp up period, particularly if it's connected to directly connected to big mechanical loads, because we don't want that motor to try and bang hit that mechanical load straight away, and it's going to take a lot of torque to get that load moving. That's like dropping the clutch in your car, right? So what happens when we rev the car to full speed and drop the clutch? The wheels start spinning. And they do on my car. Your car probably can't pull that off. The wheels start spinning. So what's happened is that mechanical connection between the engine in my car and the road is broken. It's broken at the point of the greatest weakness, which is the friction between the tyre and the road. Because I've tried to produce maximum torque and put that onto the road in a single instant. So my mechanical chain that moves the car, and the mechanical chain that gets force from the engine down through the drive shaft to the differential, into the wheels and to the road. So that I'm thinking of, well, I'm not talking about an actual chain, I'm talking about the chain of mechanical force moving from one point to another. It's broken because I've tried to hit too much torque all at once. And so we may get this with a motor as well. The motor, as soon as I put power on it, wants to go to full speed immediately. It's going to start up, get to full speed as quickly as possible. We may not want that. That may not be ideal. If we're starting up a large conveyor belt or something like that, then it's going to be a problem. There may be a mechanical method of reducing that initial starting, or that initial mechanical load We may do that with a gearbox, like in a car, or a clutch or something like that. But the electrical method of doing that would be to reduce the starting speed, and we can do that with a wound rotor with resistors in external resistors in series with our motor windings, with our rotor windings. And we can have very variable resistors or varying levels of resistance that we switch in and out of the circuit as the motor starts up to slow it down. We're reducing the current that's going to flow in that motor, and therefore it's going to slow it down. In most cases, it's not important to get full speed immediately, so we're not losing anything by slowing it down. We're also going to reduce the electrical wear and tear is the wrong word. We reduce the electrical load on startup because we're not going to get that massive inrush current. We're deliberately limiting the current. So that's what we would use a wound rotor for. We can see the torque curve here. Does it show us? Yeah, it doesn't say which one is which of those three curves, but the important thing is that, as it says there, a high rotor resistance is desirable when starting and running the motor at low speed. With a low resistance motor, the starting torque is low and therefore current is increased. So it's going to draw much more current to try and produce the torque that we want. If we have a higher resistance, then we'll get better torque at lower currents. Okay, motor enclosures. No matter whether a motor is DC type or AC, single phase or three phase, an important consideration is the type of casting or enclosure necessary to protect the motor against its working environment. Various types of enclosures have been designed to suit particular working conditions. Some common ones are. I'm going to move through these pretty quick because we saw these in the last topic. Motors are required to operate in many different environments, ranging from a well-ventilated, dust-free, weather-protected situation through to an atmosphere that's highly flammable, where hazardous vapors or gases may be present. The casing or enclosure necessary to protect the motor against its working environment determines its ability to dissipate the heat generated from within to its surrounding atmosphere. If the heat cannot be readily dissipated, the power rating of the motor must be reduced. In effect, a motor that may be rated for 4 kilowatts and good ventilation where air can flow through the motor may be needed to derate it to 3 kilowatts, or any other rating, that's just an example, if used in a sealed enclosure. Casing design and ventilation. From the diagram shown, you can see that air is circulated inside the motor to take heat to the outer case. The external fan creates an airflow directed by the cowl around the motor to assist in cooling. We will now look at some of the protection levels and methods of ventilation required for motors operating in prescribed conditions. So here we have it. That's our fan on the end of the rotor, and we saw that on the very first diagram we looked at, that we could have that fan there, and it's going to drag air in, and it's going to push air around the outside of the motor. It's going to push air through that rotor and through this little space between the stator and the rotor. So it's going to push air all the way through to keep that motor cool. Okay, we saw this one on the last one. This is a screen protected motor. The motor is enclosed in a steel casing, and the shaft runs on bearings housed in the end covers of the casing. The end covers are fitted with metallic screens, and an internal fan drives cooling air through the motor. Screen protection is used for motors in dry, dust-free conditions. It's the most common enclosure. So there's not a huge amount of protection from water or dust or anything. The screen there will stop you putting your fingers in, which it's a good idea, right? Because what's inside there? Well, that's our fan, and the fan blades might just chop your fingers off. But other than that, there's not a huge amount of protection from external things going into the motor. The drip-proof motor, which we're going to use. Okay, we're going to use the exact same photo. That's cool. The drip-free motor is a protected motor in which the openings for ventilation are positioned to protect against drops of falling water. drops of water falling on the motor at any angle not greater than 15 degrees from vertical. So coming down up to 15 degrees from vertical. So if we start coming in from the sides, then the drip proof motor is not going to work. So it basically has a roof on it, is what we're saying. The ventilation openings are not screened so that accidental contact with the ventilation openings are screened so that accidental contact with moving parts is prevented. As I said, it's a screen there to stop you sticking your fingers in. The motor is not suitable for dusty atmospheres, with particle dust could block the screen, causing overheating. So it's going to stop water dripping down from overhead. It's got a roof on it. It's not going to prevent water coming in from the sides. It's not going to prevent dust coming in either. Totally enclosed motor. As the name suggests, this type of motor has no external vents to circulate air through it and relies on the surface of the motor body to dissipate its heat. For this reason, the body has cooling fins on the outside that effectively extend the surface area available for cooling, thereby increasing its cooling ability. These motors are divided into two categories: totally enclosed non-ventilated, in which the natural flow of air over the motor provides cooling, or totally enclosed fan ventilated, which also has an external fan and counter-directed cooling air along the fluted slots in the outer shell of the motor. These motors run hotter than others that we've described, and so high temperature insulation such as fiberglass is often used. Dirt and moisture are excluded, and so this enclosure is suitable for use in corrosive atmospheres or for installation where drip proof motors are impractical because dirt, fluff, metal swarf, cutting compounds or other harmful materials are present. So they run hotter. Why do they run hotter? Because we don't have the same cooling abilities. We're enclosing that motor down to stop stuff getting in, so it'll be hotter. Here's a couple of pictures of a totally enclosed motor. As you can see, this one's a great example here. There is no external, no way that anything can get in. I'll let you pause this and read the little descriptions as required. Flame-proof motors. We've talked about these before as well. The flame-proof motor is designed to ensure that if an explosion occurs within the motor itself, the explosion will be contained within the motor and not transmitted to the surrounding atmosphere. Providing the motor enclosure can contain any such explosion, the safety of the installation remains intact. To do this, the motor enclosure, so the stator frame, end shields and fastenings, must be very robust. And as I've said in the previous lecture, go back and have a look at that if you need to. Various things about flame-proof motors that make it special. In particular, I talked about, I think, the fact that once if something very small goes wrong inside our flame-proof motor, you turf it out and you get another one, because you cannot repair it once you've opened it up. You've compromised the flame-proof protection. So in addition to that, also need extra long flame paths necessary on all mating joints. For example, end shield to frame, terminal box to frame, and terminal box lid to terminal box frame. Experimental studies have shown that the width L and gap I in figure A, where's figure A, is that the previous slide or the next one? Okay, there we go, we'll come to that in a second. The width L and gap I in figure A can have values that will not let the explosion be transferred to the outside. A spigoted joint reduces the chances of transmitting the internal explosion to the atmosphere. See figure B. Here the joint is stepped, or spigoted, to increase the flame path and decrease the width of the gap. The terminal box must also be able to withstand an internal explosion in exactly the same way as the main motor enclosure. So looking at these pictures here, this is quite neat actually. This is something I've talked about before. We have some good diagrams now. So imagine that this would be our terminal box here, and this is our terminal box lid. In this case then we have that little gap there, and when you see this in real life, it's just like smooth machined surfaces. It's quite an odd sort of thing, and a thick rim on the box with that smooth machined surface. And if you don't know what it's for, it looks quite odd. Once you realize, once you're told what it's for, it makes a lot of sense. That that gap there will be very, very thin. In fact, when you're putting those two surfaces together and you're bolting it down, in most cases you can't even tell. You won't realize that there's actually a gap there. It'll just seem like those two, as I said, those two machined surfaces just go nicely against each other. But what that's doing is creating a very small gap and a path, and then in this one here, the spigoted joint, you can see that that path is a little bit more complicated. It's got that step in it. So that means that if something happens in there, an explosion, rather than if it's completely sealed, blowing that enclosure to pieces, and then thereby releasing the explosion to the outside, the explosion has got a path to go on. So that pressure can come out, and then it's going to cool the flame as it gets out. So the theory is that by the time our explosion reaches the outside, the heat and flame have dissipated, and we are it's still going to do some internal damage to that enclosure, no doubt about that whatsoever. But the idea is that it's not going to catastrophically destroy itself in that hazardous atmosphere and then create further explosions externally. The picture shows a spigoted terminal plate and terminal arrangements for a flame-proof motor. Note the robustness of the terminal box. Each enclosure must be able to contain an explosion without transmitting it to the other. Thus, a very special terminal arrangement is necessary. These use a cast iron terminal plate with terminal studs and insulating bushes mounted in it. So we don't actually have physical wires running from the terminal box into we have the connections coming in. They'll be connected to what did it say? Terminal studs, and then that enclosure is then sealed and blocked off from the internal of the motor, but the stud will go through that seal, and then you have wires on the other side, which means that terminal box and then the motor enclosure itself will be separated with just the stud running through. So we have an electrical connection, but no connection. The spaces within those two boxes, the motor enclosure and the terminal box, are physically separate. As with the totally enclosed motor, ventilation is aided by a fan mounted on the motor shaft at the non-driving end. The flow of air over the motor cools it. Flame-proof motors are used in conditions where flammable gas may be present, such as the mining and oil industries, and fuel industry obviously uses them a lot, hence I've come across these a fair bit. Okay, next, integrated over temperature protection, thermal cutout. Some single and three-phase motors have a built-in integrated over temperature device, sometimes known as a disc limiter. This consists of a bimetal disc that is designed to perform a snap action when a certain temperature is reached. This action is mechanically connected to a switch wired in series with the motor and provides both overcurrent and over temperature protection for the motor. Figure A shows the construction of the device, and Figure B, the connection by which the motor is automatically isolated from the supply on over temperature. I'll let you guys again pause the video and have a look at those. We have talked about overcurrent devices with bimetals before, so I won't continue to go into the detail on that. Rotating magnetic field. Okay. So the natural 120 degrees phase shift between each phase of generated three-phase AC gives the necessary current phase shift. That was missing in the example of the alternating field between poles to establish a rotating field in the stator of a three-phase induction motor. So hopefully, if there's anything that you guys have kind of grasped so far about a three-phase motor and the difference between three-phase and single-phase is that the 120 degree separation of the three phases means that we have a rotating magnetic field. As this phase here, you can imagine, if this phase here is high, this one will be low, this one will be somewhere in between. And then as this one comes down, this one comes up, this one goes down, and so on. So that we create that true rotating magnetic field, which gives us that phase shift. We don't have to create that offset phase with the capacitor or whatever that we did with the single phase motor. And then the coils are connected in star to a three-phase supply. The resulting currents set up pulsating fluxes around each conductor. However, because of the spacing of the coils and the phase difference of the currents in the coils, the flux produced by each phase combines to form a resultant flux that moves around the stator at a constant speed. The resultant flux is called the rotating magnetic field. So we have three phases that are going off separately, right? They're going on and off on their own thing with a sine wave. But the interaction between the three magnetic fields creates that single big magnetic field around the rotor, and it goes in a circle. A bar magnet pivoted in this rotating field would lock in with it and rotate at the same speed. So if we just stuck a magnet, if we stuck a rod through a magnet and held the rod at each end, put it inside the stator, then magnet will just spin because it's going to chase that magnetic field that's rotating. A magnet's going to be attracted to another magnet, right? But because that magnetic field turns, then it's going to turn, kind of like a compass, right? Kind of like a compass. If you think about a compass, the magnet or the needle on the compass wants to look at magnetic north. So if I turn the compass, then the needle, with respect to the casing, will spin. The needle's going to point in the same direction. In this case, we've got the same thing. We have our rotor, or if we use this example, just a magnet sitting inside the stator, and then it's going to want to point towards the magnetic north, wherever that is in the stator. If I move that magnetic north, I spin it around and around, then the magnet will follow. Reversal of rotation. So we have our rotating magnetic field inside the stator. What if we want to reverse it? The direction of rotation depends on the phase sequence. For example, if red, yellow, blue will give us clockwise, then red, blue, yellow will give counterclockwise. So the direction of any three-phase motor may be reversed by simply interchanging any two of the line conductors supplying the motor. Note, yellow is the official phase color, but in industry we now use white for safety reasons. Okay, so first paragraph there, the important thing to note here, any change. So I change any two, I can change 1 and 3, or 1 and 2, or 2 and 3. It doesn't matter. I can change any two, I just swap them over. When I say swap them over, what do I mean? Well, the 3 wires coming in from my supply, I just take 2 of them off the phases that the windings they're connected to, I swap them over and connect them back to the phases in the motor. I can do that with any 2 phases and it will change the direction of the motor. I can change any other 2 and it will change it back the other way. That's really important to know. And again, much simpler than single phase. If you remember back to the single phase stuff, then obviously we have to change the direction of one of the windings, the start winding, but not the run winding, and so on and so forth. And note little here, we talk about the yellow phase. We don't use yellow wires anymore, and the reason is because we use green and yellow wires for earth, and therefore the yellow phase wire could confuse some people. So now we use white, but we still talk about the yellow phase. Okay, the direction of rotation of a 3-phase motor may be reversed by interchanging any 2 of the 3 motor supply lines. In practice, motor reversal is achieved by using 2 mechanically interlocked contactors. So KM1 and KM2 in this case, they're just labels, we're just calling them KM1 and 2, to change the stator connections when required. In addition, these 2 contactors are usually interlocked electrically to prevent energizing the contactor not in use. Yeah, if we end up turning both contactors on at once, then we'll get a short circuit. So we'll have some sort of interlock in there, which is not shown on here. Just pointed out that is the case. The circuit here shows a direct online starting motor reversing by inversion of line 1 and line 3. So here we have it here. If we have the first contactor on, you can just see line 1 goes straight through to U. So the first connection of the motor, right, just goes down there. Don't worry, but that's just our fuses. So it's through the fuse, through KM1, contactor number 1, straight across there, straight down there. Line 2, same thing, straight line 2 to V, line 3 to W. If I open that contactor and close this contactor, what happens? Well then, line 1 is going to go through the first terminal of the contactor and then down to W. Line 2 is going to go through the second terminal of the contactor and to V, so it's going to be the same. Line 2 is the same. Line 3 will go down through contactor terminal 3 and then to terminal U on the motor. So I've swapped line 1 and line 3, so the motor is now going to reverse. Okay, we're going to hold there. That will be the end of part 1. I'll see you back shortly for part 2, and we're going to go into theory of torque production.